Eh ben, bonjour à tout le monde. Je me permets de faire le lancement en français. Sans doute fera l'exposé en anglais, mais ça ira bien. Donc aujourd'hui, on est très content d'accueillir Josué, membre de notre équipe, euh, qui va nous parler d'un de ses derniers papiers, A Numerical Algorithm for Zero Counting for an Adaptative Speedup.
So, yeah, thank you very much. So I will be talking in English because probably if I will be talking in French, it will be painful for you and painful for me. Okay, so yeah, in this one, so this is a paper that has been accepted to Mega. At some moment, the actual paper will appear on archive once I finish the finite precision analysis. Okay, so this is a continuation by an old trilogy by Cooker, Crick, Malahovin, and Desevor. So this is a numerical algorithm for zero counting, one, complexity and accuracy. So in this one, they propose the algorithm, they do the finite precision analysis, and then they do the condition-based complexity. Then on the second part, distance to illposeness and smoothed analysis, they do the condition number theorem. This just means that the condition number that they introduced in the first part, they relate it to the distance to the discriminant. And with that thing, they do a probabilistic analysis of the algorithm using integral geometry. And then on the third part, randomization and condition, they essentially do a probabilistic analysis adapted to the condition number. So before you use integral geometry, so this means that you are using a machinery that maybe doesn't give you the best constants. Later on, they use this thing which gives you more refined constants for the complexity. So this will be like the briefing of the three parts together. So there is a numerically stable deterministic algorithm, which I usually call CKMW, that if you give to it a real homogeneous polynomial system, where each polynomial has degree di, then this computes the number of projective real zeros of f. And then it has some pairs with it, so it can be modified to produce approximations a la Smale. When f has the Cosland sub-Smale distribution, so that is the coefficients of these polynomials are Gaussians with a set in very specific variances, which are chosen in such a way that this distribution is invariant under orthogonal transformations. Then you have that the running time is like more or less simple exponential in small n and polynomial in the degree, and with high probability. So here is this parameter ya, which essentially controls. So the bigger is this parameter, the more success probability you have, but then the complexity will be growing and growing and growing. So here, this n is the number of coefficients of the system, counting counting also zero coefficients. This capital D will always be the maximum of the degrees, and this calligraphic D will be the Bezout bound, so the product of the degrees. Essentially the maximum possible number of real roots. Then it can be easily parallelized. So one can actually pass from this exponential bouncing n to polynomial bouncing n by parallelization, always at the cost of this number of parallel processors. And then it can be run with floating point numbers, which is probably the big advantage of this algorithm in itself. Okay.
Sorry, Josué, what do you mean by approximations à la Smale?
So
sorry, Josué, I had a question and I had not opened my mic. What do you mean by approximation à la Smale?
This will come now.
Okay.
You are now muted.
So this is a small interlude. So according to Fabrice, this will be the philosophy of Kronecker. So a system is solved if its root is represented in such a way as to allow the performance of any arithmetic operation over the arithmetic expression of its coordinates. Then a version of this by Ismail is a little more different. So it's like a system if solved if we have an approximation of its zero in such a way that we can improve iteratively the error of the approximations until this is small enough for our needs. So in other ways, we have a solution, and by some iterative process, we are able to refine this approximation as much as we need for whatever we want to use that roots. So here we will, in a certain way, require exactness. Here we don't require exactness, but we require that we can make our approximation as precise as we want. La clase Tonelli. And so then here, this is the definition of approximation a la Ismail. So usually what Ismail did was you take an approximation of a zero, in this case x, of a system f, and you want that the Newton method converts quadratically to x. So essentially you have an approximation where Newton method converts fast, so that you are able to get a lot of digits each time that you apply approximation. Of course, here probably this will not satisfy a constructivist like Kronecker, but that's another tale. At least for us, at least in numerics, this is good enough because you can never get an exact root numerically. Okay. So now going back, then we have some spin-off of this trilogy by Ergur, Pauris, and Rojas. So in this one, they do like a broader, so they do like two papers. The first one, a broader family of distributions. They show that you don't need Gaussians for the probabilistic analysis, although they only did the average analysis in the first part. But then on the second part, they extended it to a smoothed analysis, and they also tackle some structure systems. So if the structure of your system is generic enough, the algorithm works well. That will be very colloquially. So here, this probably the second part will not be titled like second part, but this is some to some editorial decisions of the journal they submitted the paper to. Okay. So then here, when we do the modifications that Ergur, Pauris, and Rojas adds, will be essentially this new line. So has a wide class of random distributions, and for this wide class, we have essentially the same kind of bounds. So the main point here is that the CKMW, so the algorithm by Cooker, Crick, Malachowicz, and Vesevor, doesn't have finite expected runtime. So going back to the slide, I mean, you have like this R to this. So if you try to compute the expectation of this quantity, one will realize that this quantity doesn't have finite expectation. So you cannot bound it by a finite numbered expectation. You will get infinity. So the question is, okay, can we obtain finite expected runtime? And the answer is yes, which is essentially what I do in the paper. So then the theorem is more or less very similar to what we have before. So there is a numerically stable deterministic algorithm. Now we put here a small a to indicate adaptive. The given real homogeneous polynomial system, blah, 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 blah. And now let's pass to the most important part. And you can see that the complexity bound is a little bit weird. So the expected runtime of this model will be like almost single exponential in n. Then there is this factor here, d to the n times the number of coefficients, including zero coefficients. And then here we have the Bezout bound combined with the number of coefficients. And again, this algorithm can be easily parallelized, and it can also be run with floating point numbers. So now here let's relate this to other algorithms. So in the symbolic realm, we have the critical points methods, the rational univariate representation, and the Gröbner basis. Then for implementations, all of these are more or less implemented. We have this root finding isolating maple, which is essentially the implementation of this rational univariate representation. We have the Gröbner basis library by Fourier. Then we also have this real algebraic geometry library. So in general, these are quite efficient, and the complexity is roughly d to the on. So here I'm not being very precise with the bounds that exist in the literature. Then in the numerical realm, we essentially have homotopy continuation, and homotopy continuation. So you have a lot of homotopy continuations to do. So you have total degrees homotopies, real homotopies, repeat until all. So this is, you pick a random system, you follow it, you find a root, you pick another random system, you follow it, you find another root. If this root was different, you add it to your list of zeros. If not, you repeat again the process until you find all roots, until you find all zeros. So yeah, in general, so here the idea will be you use homotopy continuation to find all complex zeros, and then you use subselect the real ones. So here we will have the implementation, so Julia homotopy, Bertini, PHC pack, in Macaulay 2, and other packages. And the main issue here is that despite we have a full solution of a Smale 17 problem, it's not so clear how is the complexity of finding real zeros, because all the methods that one does in homotopy continuations, all the theoretical results hold for a random complex system, but not for a random real system. And it is not so clear what will happen if you put a random real system, if you will get finite expectation or not, but the current techniques cannot handle this. Even use the problem of finding one complex root of a real polynomial system. This is a problem that is open in terms of complexity. So then we have this called symbolic numerical realm. So by this I mean subdivision methods. So here we have univariate methods. These are optimal. You have the paper by Pan, and then you have maybe more readable, almost identical bounds to Pan, but slightly worse by Sagralov and Melhorn. And then in the multivariate setting, things are not anymore so optimal. So you have interval Newtons, so a lot of variants of Newton with intervals. This you can find a lot of this in a book by Neumayer. Then you have a version that uses Miranda instead of Newton. This is a paper by Xu and Yap in 2019's ISAC conference. And then there are some other papers, among other papers, that are reduction to one dimension. So you do some criterion in which you reduce this finding a root to some univariate criterion, and then you check there. So these are essentially, I mean, the latest developments are a paper by Mourien and Pavon, where they show like quadratic convergence of this subdivision scheme, and then one by Manzaflares, Mourien, and Sigeritas. Then we have implementations of these subdivision methods, so globsolve, interlap, and interval root finding in Julia. And despite, okay, this tend to work reasonably well in practice, but still the complexity is not very well understood of these methods. For example, if you go to this paper by Manzaflares, Mourien, and Sigaridas, there are some parameters that their complexity depends of that is not so clear what is their meaning a priori. So you look at the parameter and it's not so clear what this, let's say what this parameter is, what's the meaning of that parameter in terms of geometry of the system. Okay, so let's go. So then the main idea is essentially to pass from a uniform grid to to an adaptive grid. So then I will give more details at this. Now this is like a very from a beer viewpoint before going into details. So this is not a new idea. So this essentially came with a work with Cooker and Ergur on the Plantinga-Wächter algorithm. And the main idea is that if instead of using a uniform grid as the algorithm by Cooker, Creek, Malachowicz, and Besever use, then we will should get an algorithm whose complexity will depend on this quantity, which has finite expectation. So this will be more or less the underlying idea. Like if you can do this, you get finite expectation. So then there was working with, if you take the uniform grid algorithm, you try to do it adaptive in the most naive way. So you use only the results that are in the uniform grid algorithm. You will get an adaptive grid algorithm, but the complexity of this algorithm will not depend only to the n, it will be to the 2n. Of course, this might not seem like a big change, but this small change is essentially the difference between finite and infinite expectation. So this quantity over here doesn't have finite expectation. Essentially, it blows up. So this was done by a master thesis of Hahn and then a master thesis of Eckhart. So what essentially are the problems? So why this does happen? So the first thing is that one uses a criterion that depends on the square of the condition number instead of use the condition number. And then there is a certain extra issue with the post-processing selection. So once you do the grid, you will have a selection of some approximations. Maybe there are redundancies, and you have to get rid of these redundancies. So process the things that you select in a way that you get rid of the extra stuff that is there, or to combine the information in a way that you can read it easily. And the problem there is that you might have too many pairwise comparisons. Okay, so the way around essentially is a very simple idea. So essentially is instead of, usually when you use beta, which is this quantity, this plays an important role in detecting if the Newton's method converges fast or not. Usually people uses this approximation and this upper bound. And when you use this upper bound, this mu here, then you will bound it by kappa, and this is why you get the kappa square, because one comes from the bound of this beta and another one will come by the bound of another parameter called gamma. So this is essentially the core of it. So instead of using an upper bound of beta, we should use beta directly, which more or less a way of thinking intuitively about beta is that this is the length of a Newton step. So this is how much Newton's method moved to the next iteration. So, and then here there are some additional perks in this thing, which will be a change of the norm. So instead of using the Weil norm as it was used before, we used infinity norm. This was taught by Felipe in a previous talk. So this essentially allows us to, instead of getting capital N to the n plus 1, which will be roughly d to the n squared, used to get d to the n. This is a very important gain. Then we can do, instead of normalizing the full system as we do here, we can use normalize equation by equation. So we normalize the coefficients of one polynomial by the coefficients used of that polynomial. So in this way, we can, instead of getting bounds where a capital D to the 2n, we substitute this by the Bezout bound to the square. So this is kind of the maximum versus the geometric mean. So if our system has polynomials of different degrees, this can be an important gain. And then similar we do with some Lipschitz constant decreasing normalization of condition. So yeah, this is more or less, like, let's say, like the peer view. So now I will pass to share the screen and speak a little bit more in detail about all the tiny, about a more technical overview. Let me see. Over here. And voila. So do you see properly the screen?
Yes. Yes, we do.
Unmuted.
Okay.
You are now muted.
Perfect. Okay, so now let's now talk about what I will call the main ingredients. So I will go one by one how this works. Okay. So before this, let me just introduce some notation that will be useful for us. So whenever I write this ND, these are homogeneous polynomials of degree D in x0, x1, xn. What else? Then I will use this weird notation. Technically, this is boldface D, but this is not seen by working. So this, you should think of this as ND1 times. So this will be like the set of systems that I will be considering. In general, in our case, Q will be equal to N. And then another extra notation that will be useful is that this will be used the matrix of the degrees. This beautiful delta. And then, yeah, these complexity parameters I introduced before. This is the maximum of the degrees. This is the product of the degrees. And this guy is the number of coefficients. So check here that, okay, I will write 1, 2, I don't think this is needed for us now. So yeah, and so I introduce some new notation. Yes. So this I will recommend that you annotate somewhere. I will try to recall it during the talk, but yeah, maybe at some moment I forget. Then I will use this guy here. Use as a way, so this guy, so now let me, so this will be like the k derivative tensor. So this is essentially a tensor of polynomials. Then I will use the notation dxk for evaluation. At x. And then finally I will use this txf just to mean. And here I use precompose this with. So you should think of this as the derivative of f at x restricted to the tangent space of the sphere at the point x. Okay, so ingredient 1. Here I will not be very long because Felipe talked about this. So this is essentially the infinity norm. So where before we were using this Bile norm, which was this this little monster here. let me write here equal to di, and here fi alpha square. We will be using what I will call infinity norm, which is a lot nicer. It's the maximum over I and the maximum over x belonging is n of fx. Sorry. If ix, and we can also see this as the maximum over x is an infinity of this guy. So here the most important result to us is this so-called Kellogg's theorem. And this is, I think, is with two L's. So Kellogg's theorem just tells us that if f is a polynomial of degree d, then this implies that dx, sorry, evaluated at v1 okay. So this is a tensor, so I can evaluate it in vectors in R to the n plus 1. Then this will just be less or equal than t choose k, the infinity norm of f, and then here use the product of the norms of these vectors. So here I will just mark the 2 to make it clear that this is the Euclidean norm. Okay. This was essentially is the main result that allows us to use this norm instead of the other one, but this essentially is what Felipe, what was the name? What Felipe was telling. So this will be the Kellogg's, okay? This is not incredibly important. Then we will introduce the following definition, which is what I will call, this is the row normalization. The row normalization, this is what I mean. Instead of dividing its guy, I use divide its guy by its corresponding norm. So the main idea of this is that if you just divide by, so this, and here is important to know that we do this instead of f divided by f infinity. So the main advantage of this row normalization is that if you do the second one, you can do a certain trick where I can reduce the coefficients of one of the polynomials, and then I get something that is badly conditioned, because one of the equations will give me always very small numbers, while the other one will give me always very large numbers. With the row normalization, in a certain way, what you guarantee is that all the equations are of the same magnitude. This will be more or less the rationale behind that this normalization makes better the conditioning. And here the main, so let me write this with orange. Of course, the exclusion lemma.
There is a question by...
So this exclusion lemma essentially says
Sorry,
us...
Josué, there is a question by Guillaume. For the W norm, isn't it rather f squared divided by di alpha?
Yes, sorry. Here there should be a d minus 1. Thank you.
You are now muted.
Yeah, that was... so exclusion lemma, the only thing that it will say us is that if these guys has a very large norm. So in this case, let me put it here this way. Sorry. So if this guy here is larger than R, then the zero set of this guy intersecting with the ball. So this is why it's called the exclusion lemma. So essentially it tells us in a very quantitative sense, if the value of my polynomial system at a given point is large, I cannot have roots around that point. The important thing here is the quantitative sense in which it says as this. This is just a consequence of this Kellogg theorem.
Sorry, here, can you come back? You have written that if your the value of your system is large, then the intersection is not void. So you have it is void. Okay.
Yeah. This is me betraying myself.
You are now muted.
Okay, so now let's go with the second ingredient. So ingredient 2. I think this, let's put it in rescale condition. I mean, this probably is one of the most, how to call it, technical definitions that one uses, because usually we will use traditional numbers. And here, I will write them with the Weil norm, just because I don't want to mix up. So usually you will find these definitions. And then here you will find this EXF tilde, this guy. Here let me put 2, and here 1/2. And then you will find the kappa fx, which is essentially more of the same thing. So fx square divided by the norm of the veil square plus, and then here you have this mu x minus 2, and here to the minus 1/2. So these are the traditional ones. So here you can see that there is this thing. And then what will happen is to rescale. So with Felipe, we saw how we can substitute here the Weil norm by the infinity norm. But now I do some rescaling. So let me write this. So I call these numbers nu of fx. So this will be essentially f infinity. Here I essentially do the same. Here I use put delta square. So now I will explain why. So with Felipe, if you remember, here was only delta. Now I'm adding a square. This will come clear now. And here I will use put infinity 2. So this goes from the, this thing will go from an Euclidean space with infinity norm to the tangent space of x that has the Euclidean norm. And then I will use define my kappa x using here I'm using a norm. Here I will use the minimum. And again with very weird rescalings. You will see that I'm adding this here. use because I can. So where before I have mu, now I will have nu. Where before I have kappa, now I have this C. You can convince yourself that this is more or less this here where I'm using the L2 norm, here I'm using the infinity norm. That's it. And then I adding weird scalings with delta. So the advantage of this, essentially, so what's the advantage? Is essentially that F mapping to let me write will be still one Lipschitz. It's even something stronger, but I think this is too technical. And the main advantage is that this map here, with this belonging to Sn, is one Lipschitz. So if you remember the thing with Felipe, this was not one Lipschitz. This was the Lipschitz in the talk by Felipe. So adding here this matrix, we get one Lipschitz. So the advantage is that while this is one Lipschitz, more or less we will get the same, but then instead of getting the maximum to the n, we get the product of the degrees, which for the mixed case is something that will give us advantages. So this is just like this tiny technical thing. And then, the important thing is, one motivation for these numbers is, for example, the following one, that is, let me write it in a way, smooth, or if you want to call it regular, if and only if the supremum over x belonging to Sn of Cfx is less than infinity. And then another thing that will happen that is also very nice is that this also happens if this expectation is finite. Here we are using the Lipschitz property. This follows by Lipschitz properties of what you should think is that when you integrate something like 1 over x over 1 over x to the n in an n-dimensional space, you get infinity. So that will be more or less the rationale for this. So it's a good condition number because it controls the thing that the good case, because here the important thing is this is a numerical algorithm. It will not work for all inputs, but the complexity will depend on this condition number. So this is always very important to have in mind in this numerical setting. Okay. And now let's go to the third ingredient, which again is just a technical refinement. This is what I call delta theory. So let me recall you Newton's method. So the spherical Newton method. So you have, of course, this is not always defined. You have x, and this x will just go to x minus dx fx divided how we should think about this. Let me put in pink. This will be Sn. This is your point x. Here you will have a vector. This vector will be minus dxf tilde fx. So then what we do is we translate x by this vector and then we project it onto the sphere. So then this guy here will be nfx. So from here, for example, you can see the thing I was saying before. So the distance in the sphere between x and nfx is equal to the arctangent of the length of this vector, which was beta fx, and beta fx was equal to this guy. Let me put here the 2 to let it clear. So this will be so this is how you compute the distance. If I want to see how is this the size of a Newton step, I have to look at beta and then computing arctangent. Good thing of the arctangent is that the arctangent of beta fx minus beta fx is less or equal than 1/3 beta fx to the cube. So if beta fx is small, more or less the arctangent and the other one are similar to a very high degree. Because beta so x is not is a very good approximation of the arctangent. Okay, but that's just a technical thing. So now, okay, so I have introduced beta. Okay, this I usually write it so that this is clear. Remember that this is the pseudo inverse, this cross. So you can think about it as the inverse, that is in the case of the zero-dimensional case. So then there is this gamma fx. This was done by Smale. So this is this monster here. No one likes it. That's what we do. Sorry, this is not my notation. This is my notation. And here, 2, 2. And this is the, let's call this is like, this is kind of a bound on the growth of the series. And then gamma, Smale defines this gamma that is just the product of beta fx and gamma fx. So here you can see that this was a very original nomenclature, alpha, beta, gamma. So then the usual theorem, so this is the Smale's alpha. Smale's alpha theorem is essentially the following one. So we have this guy here, blah, blah, blah. We have a point in the sphere. Then what it says is that if this guy here is less or equal 73344, whatever is this, then this implies that these guys here, let me recall that this guy is defined as so this is just that I'm taking k iterations of the Newton's method. This guy will converge to the zero set of f. And more importantly, because I mean, yeah, convergence, this doesn't say us a lot. The most important consequence is that the distance in S between what's the name? Let me review what is the bound I want to give you. Yeah, let me give you the bound. And the bound between x and the zero set of this guy, where I converges, it will be at most 1/17 blah 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 beta fx, which I can also bound by 2.04 blah blah blah, and here divided by gamma fx. So important thing of Smale's alpha theory is it tells us this guy converges quadratically. I will not write technically this condition. So this usually means that when you consider iterations, you have a power of 2 to the k in the exponent of decreasement. And it tells us that something is near. But you can see here that this is a sufficient condition. So it doesn't tell us about when does, so if the alpha is small, then my thing is a good approximation of something, but it doesn't tell me the reverse direction. And for the reverse direction, what one can do is the following version, which I will call it, and this is essentially the main, let's say this is the main idea of this paper that I wrote. So the converse alpha theorem, which is we are on the same circumstances, ND, Q, we have some point in the sphere. And then the idea is if my distance, so if I know that I'm near, so before it was if alpha is small, I'm nearby. Now it is if I'm nearby, you can see here that this is this gamma versus this distance is very similar to the what's the name to the condition before. Let me go before. So before I had the distance of x to the zero set is a constant divided by gamma. So gamma times the distance less or equal that certain constant. Now I'm saying if the reverse of that, so if the conclusion of converse alpha theorem holds a little bit stronger, then, and here this is the important thing, beta fx less or equal than the distance divided by 1 minus gamma fx distance to the zero set of f. And this thing can be used to, and this is the thing that in a certain way we use, because we will refine our grid long enough so that we know that if the alpha criterion fails, it's because our point is far away from a root. Because this thing here can be translated in such a way that we have, I multiply this by gamma, and then I have this thing here. So gamma fx, distance one minus gamma fx, distance of this. And the important thing here is that this is telling us that if the distance to the zero set is small enough in terms of gamma, then the alpha criterion holds. This is the important thing of this thing that I'm saying. One could do this instead of using what I will now define as the delta theory, but then you will essentially start getting d to the n into the bound, because you cannot bound this gamma without the maximum degree appearing in the bound. Because the higher derivatives, you cannot get rid of them. And this forces the degree to appear. So then essentially what I'm calling the delta theorem, this essentially is in honor of this. I'm doing it because of the due. I mean, this is more or less following the arguments in his book. What I'm doing is, I'm saying is, okay, same setting as above, as before. ND, Q, X belonging to Sn. So if delta Fx, which is equal to the nu, this is the nu I defined before, with the infinity norm in it. So if this guy is less or equal than this monstrous number here, then, okay, yeah, this guy converges. And the convergence is quadratic. By this I mean, let me now write this precisely so that you at least understand what I mean by this, in case that you are not familiar with this term of quadratic. So here, okay, some constant, I don't care about this, and then here I will get 1 divided by 2, 2 to the k minus 1 of the original step. So here you can see, this is 2 to the k. So at each step, this guy descends not exponentially fast, but doubly exponentially fast. And this essentially is the 10 quadratic. In each Newton iteration, the number of decimal places will be doubling. So at each iteration, I will get double the precision in terms of the decimals that are in my correspondent. And then, of course, I have the converse, which in this case is a slightly more simple. It's saying if this guy is finite, then this guy, the distance of, okay, and here 1 plus 1/2 nu fx distance. I mean, here it's important to know that in a certain way, this guy doesn't have as many higher order terms as with gamma. With gamma, I was getting 1 minus something. With when you expand in Taylor expansion, it will have a lot of higher order terms. Here, I don't have higher order terms. Okay, so these are more or less the technical ideas. So I'm substituting one by the other because this is more convenient for my analysis and gives me slightly better bounds. And now let's go what I mean by this grid. Ingredient free. Let me see how I go of time. So the main idea is, here is, while before I was just having my grid on this shape, then if there was a failure, imagine that my failure was around here. Then I will just substitute this grid by the following more finer grid. So this is like the non-adaptive philosophy. And the adaptive philosophy. I will just preserve the grid as it was. But here that there was the failure, I will substitute that point by these 4 points. So in this way, I'm wasting less, let's say, less computation. More or less, the idea of the uniform thing is you find a mistake in a page, you erase all the writing you do, you start again. The adaptive is, okay, you find a mistake, you try to solve this mistake in that local region of the document without throwing away everything that you already had. And essentially what the algorithm will do, so here now let me show how these ingredients goes together. In a very, this will be like a very, how to call it, very high overview. So usually what you will do first, so I will compute the infinity norms, I will do the normalization, I will do this. So I will do exclusion test, which this essentially, the question here is there not a route around? So if the answer is no, okay, there is not a route around, so I throw away this point because I know there are nothing around here. Then what I do is the thing of, how to call it, inclusion. And here I'm doing first 2 questions. So, is the alpha criterion, well, let me call here delta criterion instead of alpha criterion. Is the delta criterion sufficient in my neighborhood? Sufficient and necessary? If the answer is yes, then apply delta criterion. So if the delta criterion has a success, there is a route around, I keep the point and I pass it to my approximation set. If there is not a point around, then I know that since the delta criterion in this neighborhood is also necessary, it means that there is no route around. And if these 2 fail, then I use refine. So I substitute this point by points with the smaller neighborhoods around. So this will be more or less the cycle of the algorithm. Now let me use end this.
Sorry, the inclusion test fails if you cannot say there is no route, but you are not sure that your Newton method will converge quadratically to a single route.
This is the thing. Since we are considering the points with a radius, here it was. So if my point is far away from the thing, it means that there is not a route in that neighborhood.
Yeah.
So this essentially, this guarantees us that if this delta thing, if this thing fails, maybe with a different constant, then I know that there is not a route, because otherwise the delta criterion will have hold.
So you have 2 constants for delta. If you have 2 constants for delta, the one for the first theorem and the one for more or less given by the second theorem.
Yeah.
And
so the thing is, with the second one, what you do is, if the delta criterion fails, so let me write somewhere, because otherwise this is just so this, imagine this is the point X with my radius R. Okay. So then, so I'm here in this inclusion test. Let me write here inclusion test. So here this says yes, and then here this says no. So the inclusion test holds, then I know there is a root. Sorry, put me. Is a root in, and here this is the difficult thing. You get X, but you get something larger possibly. You get something of the form 2 beta fx. While here, if it is not, you know, okay, there is no root in X with R. So usually when you determine that there is a root, you determine that there is a root maybe in a larger space. If not, you know that in the ball that you were considering, there was not a root at all.
Okay.
So this is more or less so this is the important thing of this converse thing, because since we will refine, this is why first we ask this question: is the delta criterion sufficient and necessary in my neighborhood? Because this essentially allows us then to say, okay, now I can use this as a I take or I reject. Yeah, so I want you to finish with what I mean by the randomness model, because otherwise it's very hard to understand randomness model. So here, usually there are 3 probabilistic properties. Let me call P1, P2, P3. So the first one is how we will call centered. So this just means that my random variable, whatever is this, has average 0. Then sub-Gaussian. This just means that for every L bigger or equal than 2, I think here is, sorry, you don't need 2, but 1. The expectation of my random variable to the L, here I take the 1 over L, then this is bounded by some constant, something that depends on the square root, and then anti-concentration. Which means that essentially the probability that my root for all t, this guy less than epsilon is less or equal than 2 rho epsilon. This is equivalent to density bounded by rho. So this is more or less like the essential properties of a Gaussian, for saying it like this. A Gaussian is good because it's centered, because it's sub-Gaussian, and because it has anti-concentration. This would be more or less how we abstract this. And with this abstraction is what then we define definition a dobro random system is a random system. And here we use write let me write di alpha ci comma alpha, here 1/2. Let me not forget about important things. X capital alpha, here some I. So it's a random system where C alpha is centered, sub-Gaussian, and has anti-concentration. Sorry, I forgot something very important. Psi I alpha are independent centered, sub-Gaussian, and have anti-concentration. And this is the model that I have. Then you can add this, what was the name? This smoothed model, smoothed dobro, where you have some fixed so smoothed dobro Q, let me call it like this, where you have some fixed polynomial fi, and then you have this sigma, then the norm of this guy, and then here you have like the gi where this guy is dobro. This will be the smoothed dobro. So the smoothed is like kind of when sigma goes to infinity, you recover the previous model I talked about, the average case. But this is kind of saying what happens when you take a fixed input and a random perturbation happens to it. So this is essentially what you get. And yeah, this is why I don't want to enter now in giving very precise bounds, because the rest of this is just proofs and proofs and proofs and technicalities. So voila.
Okay. So, thanks for the talk.
For you listening to me.
Other questions in the audience? Well, maybe I will wait a bit for questions. So you have a lot of thanks and Fabrice talking about random things. Well, maybe I will ask a question first. In Felipe's talk, there was a problem of estimating the infinite norms and of systems and so on.
Yeah.
Here the same problems appears, or the one Lipschitz condition maybe helps to estimate for neighbors?
Let me go to the slide. So here you can see that this complexity estimate is a little bit weird.
Yeah.
Because on the left you have t to the n, the maximum. This is because of the estimation of the infinity norm.
Okay.
I cannot make this don't depend on the capital D. While then, once you have the infinity norm, whatever you get only depends on the Besu numbers, doesn't depend on the degree, maximum degree to the n.
Okay, so the first term is this infinity norm.
Yeah, this is used because of that infinity norm, and then the other one is so the other one is more the random thing. Like you will always get at least this complexity, this left summand.
And it can be of the same order as the second one, or even bigger. For some systems, most of the times is put into this estimation.
Yeah, sometimes I think, yeah, I wrote it like this because it's very hard to estimate when this Besu number or when this t to the n, because this is Besu number to 2.5, so there is kind of a balance like there, like if all the degrees are equal, then the right-hand side term is the bigger one. If we are in the unmixed case, then this is the case. In the mixed case, this is more subtle, let's say.
Okay.
So I have a question. Hello.
Hello.
So it's about so you didn't say it explicitly, but it is about the. I think it's okay. So for the condition number C. So for the condition number K, big K. So in the paper number 3, if I so there was a bound saying something like with a high probability, this number K is less than Bose bound power 2 or something like that.
Yeah.
Some other term. So do you have the same kind of bound for C, for big C?
Yeah, I think you can get the same kind of bound. Maybe. So what was the thing that you obtained? So yeah, I have the bound and the expectation of the logarithm. It should be something of the same order as the one that they get in the third part. So it should be similar, maybe with an extra n, but should be similar. So with high probability, my C will be like the sub-bound 2.5 to the 2.5.
Okay, yeah. So, and this is how the 2.5 appears in the complexity, in the running time complexity?
Well, here is more, at least in this case, it's a little bit more tricky. I think initially I was thinking it might be 2. But yeah, essentially it comes from the condition number, because you have this square and then another, so a square appears because of the condition number, because of this delta square that is inside the normalization. And then another half appears because, what was the reason it appeared? I think it appears because you need this for the proper normalization, for the map to be an orthogonal projection. So I don't remember exactly what was the reason, but I think that's the reason it appears, because it appears for some reasons of the. So one is because of the delta square, and the other one is because of the norms that are in the condition number. Because it's norm, you will have a square root of d of the degree, and then all of this multiplies, and then this gives this Besu number, a square root of the Besu number.
Okay. Thank you.
Welcome.
Okay, are there any other question? So maybe I have the same question I asked Felipe, because it seems close enough. Do you think you can say something with other norms? It could help you to tackle this complexity problem? Or do you have other plans for other norms?
I mean, it might be. I mean, the only thing you need is, where was it? I think I went too much in the wrong direction. No, this was another thing. So the only thing you need is this. Let me open this so the only thing you need here is this analog of the Kellogg's theorem. So the Kellogg's theorem used to tell us that you can control the norm of the derivative in terms of the norm of your polynomial. Mm-hmm. So as long as you have such a bound, you can do the same kind of analysis that I'm doing for these algorithms or for the algorithms that Felipe talked about. So the important thing is this bound, like how is the quality of this constant? It might be that for the infinity norm, maybe you don't need to go up to the infinity norm.
Okay.
Because yeah, I mean, we are just saying, yeah, you pass from an L2 norm with a very big scaling to the infinity norm. Maybe there is something that you have in the middle where you get some balance. But I think I didn't found any analog of the Kellogg. Well, I found an analogs, but they are written in a way that is very annoying for complexity. Okay. Like, there is an absolute constant that depends only on the dimension such that this happens. But then you look at it and you're okay. this absolute constant that depends on the dimension might be very bad.
Yep. And those analogs have been done by the complexity community or by some other community for other reasons?
From this community, this essentially is the community that follows the work of Kellogg. So it's people in functional analysis, and they are interested in this problem. I really don't know. I think it's for a point of view of approximation, because this allows you to control the approximations of the derivative. But that's the only motivation I found. I mean, you can even find very weird results. For example, this Kellogg's inequality for the infinity norm, it holds in a manifold. So imagine you have polynomial functions defined that you restrict them to a manifold. Then you have that the maximum norm of the derivative is bounded by the degree times a constant times the maximum norm of the polynomial on that manifold. If and only if the manifold is an algebraic variety.
Oh.
No, you have this result, which I think is pretty weird result. Like you are like, who will tell me that this is a way of characterizing algebraic manifolds? Like I found a lot of these results that I really don't know. Yeah.
And since you have already played with the norms, have you tried to take like hypercubes instead of spheres? Non-cubes, but the boundary of a cube. I don't know how we...
Yeah, I mean, this we did. What was it? We did this with Elias. We did this for a Isaac paper. We did it in the case of one guy, and then you can get rid of these square root scalings. So you can just get the coefficients without any scaling, and then you work directly on the cube. And then certain things are a lot more easier, because you are defining this on the cube, you are working on the cube, everything happens on the cube. And for example, in that case, you can even get a halt on the support. Like here, it's very hard to choose the support. So if you do this same business I did here, you will do this on the boundary of a cube. So you will get rid of this weird square root of the combinatorial number, which is always a little bit weird. And then you can restrict the support of your polynomials as long as you have the vertices of the simplex and the free adjacent vertices. So you can consider any support that contains like the support is essentially a simplex, but you can empty it inside for your probabilistic analysis, which gives a lot more general result than here, because here I'm just handling a dense system, which in practice you will not find a dense system. I mean, this is...
But it is not worth taking this model in those algorithms.
It's worth, but yeah, this is the thing that if you try to put these two things together, you will probably end with, instead of a 60-page paper, you will end up with a 100 pages paper, and then it's like, no one will read this.
Okay.
And this is just technicism under technicism.
Yeah. But at the end, Newton method is easier to perform in subspaces instead of spheres, of along spheres. So.
Yeah, I completely agree.
Okay. At some point, Fabrice was writing something, but Fabrice, you never hit the enter.
Non, c'est ok.
C'est ok.
J'allais dire que j'ai réussi à suivre malgré tout. J'ai le CP en parallèle, donc je suis le CP d'une oreille et Bon, c'était parfait. Par contre, je suis pas intervenu parce que c'est compliqué d'avoir la stéréo dans les oreilles.
Non, bien sûr. Ok. Bon, de toute façon, Josué, on peut lui poser des questions si on veut. On le connaît, on sait où le trouver. Donc peut-être que si personne d'autre n'a de questions maintenant, on pourrait s'arrêter là et puis continuer cette discussion à d'autres moments. Pas vraiment à la salle à café, mais peut-être à des cafés du midi. Ok? Donc, bah, merci Josué. Je vais arrêter
Merci.
l'enregistrement et